Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are in chapter 8 and we have been exploring approximate methods that allow access to non-perturbative regimes of the coupling constants. We have looked at the Feynman variational principle, which needs a well informed Hamiltonian to start with some set of parameters which you optimize to get a good bound on the free energy. But as you will see, the method of choice is mean field theory, particularly useful for obtaining the overall phase diagram of several models. The main message that we got by the study of the Ising model using these methods, both the Feynman variational principle as well as mean field theory, is that we do get critical exponents which are close but not exactly equal to the experimental critical exponents in higher dimensions. In lower dimensions, both these methods fail quite badly. This is because it predicts that there is a broken symmetry phase, say for example in one dimension, which we know from the exact solution does not exist. And in the process of working this out, we realize that there is a deep connection between the liquid gas problem and the Ising model. So this was a puzzle that we posed in the last meeting, but we did not fully resolve as to why you would have such a nice agreement. So in the remaining couple of lectures of this chapter, we will look at some experiments on superfluids, and we will try to start from some set of experiments on superfluids and try to construct a model, and we will try to solve the model and try to see whether we can match the experiments. So this is the plan for the next for this lecture and the next. But it is not a good idea to leave these puzzles unresolved. So what we will first do is we will try to understand why is there such a noticeable and clear similarity between liquid gas and Ising magnets. So let us just first revise the phase diagram. So what I am showing you here is the magnetization in the HT plane, and if you run along the H is equal to 0 line, which is the line in which you have Ising symmetry, if you apply magnetic field you do not have that symmetry. You will see that as I reduce temperature, I will encounter a critical point at which an order parameter will emerge below Tc, and then you will be in the magnetized phase. You can be in the plus or minus magnetization phase, and that is as the spontaneously broken symmetry. The important thing to notice here is that you have to fix two parameters, namely the magnetic field H and T to be Tc to get to this critical point. The other noticeable thing is that you can go from the plus magnetized phase to the negative magnetized phase without actually crossing the phase boundary or without undergoing any phase transition. Now let us look at the liquid gas story. I must add one more thing here. So if you look at this Ising magnet, you will see that this line at H is equal to 0 is a line of first order transition in the following sense, that if I am at some low temperatures, let us say T by Tc is 0.5, if I am in this down polarized state here with a negative magnetic field, if I reduce the magnetic field to 0 and then go to positive magnetic fields, you will see that I will change the magnetization abruptly at H is equal to 0, and that corresponds to a first order transition. Okay, now something very similar happens here, in that you have, if you want to go from the liquid to the gas or gas to liquid, you have to encounter a first order transition in precisely the same way we did this here. Second point is that if I want to access the critical point, I have to fix two parameters, namely the critical pressure and the critical temperature. So you can see that there is this very deep similarity between these phase diagrams, and in both cases the critical point, this point here and this point here, they appear at the end of the first order line. So the first order line ends here, and that is where you get the critical point. Okay, so you can push this much further, as I will do. So, we obtained from our calculations that both systems require two parameters to fix and attain the critical temperature. We have discussed this just momentarily, and at Tc, if you look at what is the response here, we looked at this in the last meeting, in the last lecture. You will see that the response magnetization to apply to a magnetic field will scale as h to the power 1/3. So, if you simply formally do this calculation d delta m by d delta h, you will see that that goes as h to the power 2/3, right, h to the power minus 2/3, right, when I take a derivative of this. Now, if you work out what is the compressibility of this gas around this line here, you will see you will get exactly the same 2/3 exponent here. So, it is as if that the pressure here is like the magnetic field. So, if you are along some line here, you see that you are, it is like mapping this region to this region. So, there is a little bit of a tilt, but that is the only difference in some sense. So, within our calculations, we always find that these two systems have the same critical exponents. We know that the beta is same, the gamma is same, and now here delta, effectively delta is also the same. So, what we are noticing is that within our framework, one we calculated using the model in a continuum of interacting particles, and the other a set of sites on a lattice. At each site we have an Ising spin and they interact with each other, etc. Yet we get the same critical exponents. Now, experimentally, both these systems are known to have same critical exponents. They have been studied extensively, and we know experimentally that they have the same critical exponents. But they are different from what we find. We get different answers, but the fact that they are same is common to both experiments and our theory. Okay? So, this is what we have found so far. So, the natural question we would like to ask is this an accident, or more important question to ask is, how is it that the critical point seems to forget what the system is made of, in the sense that in one case it is these Ising spins sitting on a lattice, and on the other case it is particles moving in space and interacting with each other. So, how can we connect these two, or is it just an accident? So, what I am going to show you is that I can start with a model for the liquid gas problem, which is defined on a lattice, and I can actually convert it to a problem in I can map that problem to an Ising model. Okay, so I am going to go through that now. So, in our analysis of the liquid gas model, we had interacting particles in some volume V, which is L to the power d in d dimensions, where L is the size of the cube that we are using with periodic boundary conditions. So, the most important observation to start making such a model is that the kinetic energy contribution to the partition function, which is the integral over the momenta, they will only contribute an analytical piece to the free energy. What do we mean by analytical piece? That piece that is contributed from the momentum will not contribute to any phase transition physics, because it will always be analytic, it will be smooth in all regimes of temperature, etc. So, such terms that you can add to free energy which are analytic and do not contribute to anything to this sort of phase transition physics are called non-analytic, they are called analytic terms, or they are also called as background terms, right. So, that is just a background, it just shifts some energies and things like that, but it does not contribute to things like critical exponents. So, what we are going to do is we are going to develop a model ignoring kinetic energy. So, what is the model we are going to develop? We are going to say that I am going to take this L to the d volume, and I am going to dice it up into little cubes generalized to arbitrary dimensions with size a. So, for example, this here the cube area would be a square, because I am in 2 dimensions. If I am in 3 dimensions, it will be a to the 3, and if I am in d dimension, it will be a to the d. So I'll get this into some set of sites like this. So you can just, the simplest thing you can do is think of a d-dimensional cubic lattice. And what I am going to do is I want to model a dilute concentration of particles moving around, and I do not need to worry about the kinetic energy. So because the kinetic energy is not important for my for understanding the phase transition, etc. So what I do here is I say that there are a set of degrees of freedom that I am going to attach to each lattice site, and these are called nu I. So if there is a particle which is indicated by this dark color here, or some reddish color here, that at that site the nu value will be 1, that means there is a particle there. So for example, at the site j there is no particle, so nu j is equal to 0. So if you give me a set of particles and I place them on the lattice, I can give you a configuration of these particles by specifying the nus, right. So this is what we have done. We have introduced the cubic lattice and we have introduced these variables, which I will call bit variables because they are 0 and 1, where nu I equal to 1 has a particle, and if there is no particle at that site I, the nu corresponding to that site will be 0. So I can get a configuration of this lattice gas. So this is called a lattice gas, and the term here is the set of configuration is actually just the set of nu i's associated with placing atoms on different sides of the lattice, particles on different sides of the lattice. Okay. So in this slide what I am going to show you is I am going to show you that the lattice gas model can be mapped to the Ising model. So that is the interesting thing. So what we are going to do is we are going to introduce two new energy scales. There is an energy scale U0, this is the energy if the particles sit on two neighboring sites, and then there is a chemical potential for the particles. And if you think about the interacting particles model, this is exactly the set of things we had. We had a potential of interaction between the particles, and we had the chemical potential was the other scale. So now I am going to write down a Hamiltonian which says, how do I check for interactions? I say that if I am on nearest neighbor sites and if nu I and nu j are the variables which describe whether there are atoms on sites I and j or not. If for example I and j are nearest neighbor sites and both of them had particles, and both nu i's would be 1, and I will get some energy U0. You can choose whatever convention you like, but we have chosen it in this way. Okay, so it is describing some short range interaction between particles. Mu is the chemical potential, and it will simply sum over nu I will give you the sum number of particles. So this is the usual chemical potential term. So how do I determine mu? I can determine mu by saying that if you give me the density of particles n0, which is what we did when we did the interacting particles model, you would get you would want to get n0 times a to the d. So that will be the average number of particles per site. So what I will do is I will compute the average number of particles per site using this Hamiltonian. Let us say I can solve it, and then I will enforce the condition that the average number of particles is nu I equal to n0 a to the d, and that will give me an equation for mu which I will be able to solve. Okay. Now my claim is you can take this problem and map this problem to an Ising model of spins. How do we do that? So what you do is you say that you identify the state at a site with one particle, you say has spin equal to +1, that is like up pointing spin, and nu I equal to 0, there is no particle there, and that corresponds to spin equals -1. So that is a down spin. So that is the mapping, and you see if I use this formula nu I is 1/2 1 plus Si, then if you give me a set of nu i's I can solve for the Si, and vice versa, if you give me an Si I will solve for nu I, right. So there is a 1-to-1 mapping between configurations. And now what I can do is I can take this expression and stick it into this, and I will see that I can convert this problem into the problem of spins. and you will see that the mapping will force the exchange constant of the new Ising model to be u0 by 4 and h is d u0 plus h by 2, and the constant term here is some constant that comes from the extra terms like this 1 etc. that comes up, it will show up as a constant. Okay. So what we have managed to do is we have managed to show that the lattice gas model gives rise to an Ising model. That is a very important step forward, but you have to also know that the lattice gas model gives us all the van der Waals equation of states etc. That if you just work on this a little bit, you will be able to show that the lattice gas model does indeed produce for you the van der Waals like equation of state etc. So now you can see this very clear connection between the Ising model and the liquid gas problem which we solved using the continuum framework, and you can see somehow that you can say that the lattice is sort of forgotten in this whole game, and the degrees of freedom that made up this problems, mainly liquid gas rising, even that is kind of forgotten, and some universal physics has emerged. And so in systems where there is these sort of connections, you will be able to see that their phase transitions will have the same kind of properties. Okay. So this is actually a very important point to understand, like how you see the similarity between apparently very different systems, particularly when it comes to regimes near the phase transition point etc. Okay. Now I am going to change gears and I am going to start talking about superfluids. So let us ask ourselves some questions that we have been asked in an exam. So you have been asked like what are the phases of matter. So your answer will depend on variety of things. So one answer is you will say that it is a solid liquid and it is solid liquid and gas if it is a 3-mark question. Now it is what if it is a 4-mark question? Of course then you have to add that there is a superfluid. Now something for you to think about it is what will be the answer if this is a 5-mark question, what are the 5 different phases of matter, okay, alright. So you think about that. So I am going to show you in the meantime very interesting set of experiments on helium. Helium is a remarkable element, it is very light, it is not very heavy atom, it has got 4 nucleons and that is it. It has 2 isotopes, this is what we should remember. There is 4 helium, that is the one that I mentioned, it is a boson, and there is also one with 3 and this is a fermion, because if I have 3 spin half fermions, then of course it will be a fermion finally. So these are the 2 isotopes of helium and we can put them to good use, as you will see. Let us just start our focus on helium 4. So helium 4 is usual gas at room temperature, it is a very nice ideal nearly ideal gas at room temperature. If you take it down to temperatures, it still remains like a very nice gas, there is no problem, and you have to take it to really low temperatures to see anything interesting there. And what I mean by really low is something like 3-4 Kelvin like that. So in that regime of 3-4 Kelvin, and this is the pressure here, you will see that there is exactly the liquid gas phase transition etc. and the critical point etc. in this system as well. So it is just the same system that we have studied, but with some different intrinsic energy scales that forces the Tc of the system to be very low. That is basically what we have here. Okay. So if you come down at ambient pressure like 1 atmosphere, you will see that at about 4 Kelvin helium will form a liquid, helium will liquefy, right, that is the liquid gas first order transition, the condensation transition. So it is just a usual liquid, but something more interesting happens when you take it down further lower in temperature, and as you see in this phase diagram that is shown here, you will see that there is a regime called a superfluid, and that shows up at something like roughly 2 Kelvin. So let us see what is this story about superfluids. So this is the same phase diagram that I have plotted here. So this is the liquid gas phase boundary, and if you come down to a temperature which is something like 2.2 Kelvin, and if you measure the specific heat, you will see that there is a divergence in the specific heat which we typically associate with some kind of phase transition. And if you look at this, you obviously think that this is the Greek letter lambda, and because of that this transition got the name of the lambda transition of helium. And so what you find is, at any pressure, if you reduce temperature, you will see that there is a lambda transition and you go into the superfluid helium phase, which for any reasonable pressure, like definitely at atmospheric pressure 1 bar, you do get this. Okay. So what is the speciality of the superfluid? The speciality of the superfluid is that it can climb walls. If you had a coffee mug made of ceramic, coarse ceramic, if you pour the superfluid in that, it will just flow through that. Like a conventional simple ceramic mug cannot hold a superfluid. It has so little viscosity that it can just flow through the pores of the ceramic. So it seems to lose all viscosity and become something that flows without dissipation, if you wish. So this was discovered quite a while back, and it is one of the most fascinating things that is around, and if you wish, you could search the internet for videos of experiments on superfluids, and I am sure you will have a great time watching them. Okay. So now the question is, we would like to understand how to think about the superfluid transition, and I have multiple reasons for bringing this up, as you will see. Let me advertise at least one of them. So far in the course we have seen only discrete symmetries like Z2 symmetry and so on, and symmetry breaking of Z2 symmetry. So I will show you that in this class of transition you actually break a continuous symmetry. So this is one of my motivations, and there are other motivations which will become evident as we go through the lecture. Okay. So what we are going to do is, we are going to think of this collection of helium atoms as a set of non-interacting bosons, okay, and let us say that the density of these is given to be rho. Okay. Now what we are going to do is, we are going to construct a continuum field theory to describe these bosons. So what do I have? I have my arena is the d-dimensional box with periodic boundary conditions and so on, with volume V, and I model these bosons by creation and annihilation fields which are called phi x and phi dagger x. So if I take the what is called as the vacuum state where there is no boson, and I do a phi dagger x on that vacuum state, I will create a boson at that site, at that position x, and you will have one boson in the system. So this is the Hamiltonian which describes the kinetic energy of these bosons, and mu here is the chemical potential and m is the mass, and I have chosen units where h bar is 1. This is very standard in people who do theoretical physics particularly, right. And important thing, how do I know that these are bosons? You will find that, okay, there is an error here, this should be a minus sign, it's this, please note that there is a minus sign, we will correct it in the notes. So this should be a minus sign, actually the minus sign should come here, I will fix this. So just it is the boson anti-commutation relationship has to be there, sorry I am sorry, the commutation relationship of the boson has to be there, okay. So the important thing to note is that if you take this bosonic Hamiltonian, you will see that it has a global U1 symmetry. Now what do we mean by U1? U1 is the set of all complex numbers with unit magnitude. So if you multiply any two complex numbers with unit magnitude, you will get another complex number with unit magnitude. 1, the number 1 is a complex number with unit magnitude with 0 imaginary part. So that forms the identity. For any complex number with unit magnitude, there is another complex number which is the complex conjugate which when you multiply with it you will get 1. So that is the inverse, and therefore I have formed a group out of unimodular complex numbers. So this group is called as the U1 group. Now what is the symmetry? The symmetry is that suppose I were to take this phi of x and transform it by multiplying by a phase e to the I theta, then I will be able to leave this Hamiltonian invariant, as you can immediately check. So what this means is that my system has a continuous global symmetry. Now I am sure that in your classical mechanics courses you would have studied the consequences of having continuous global symmetries. So continuous global symmetries will imply by Noether's theorem some sort of conserved currents and so on, and what this means simply put is that the total number of particles in the system will be conserved. That is what is called as a Noether charge, right. So this will be conserved. So you do not, if you put in n bosons, there will be n bosons at any later time if you evolve it by this Hamiltonian. That is what it says. Okay. So this is the consequence of the U1 symmetry of the problem. Now we have set up our system in such a way that there is a chemical potential and there is a set of there is a kinetic energy and so on, and we said that the system has some density of particles which is rho. Now what you have to realize is that whenever you are given a density of particles, this is number density, that will correspond to a length scale. The reason is that density goes by 1 by average interparticle spacing to the power d, where your d is in spatial dimension. So you will see that from the density I can actually construct a quantum mechanical energy scale. So that is h cross square, some de Broglie wavelength like quantity, h cross is 1 here, so that is why you do not see h cross, divided by 2m. And so you see the de Broglie wavelength is exactly what we have used here. So inverse de Broglie wavelength will be like some de Broglie momentum, and that is what we have used as rho to the, so that is the momentum square. So that is rho to the power 1 by d, something like a de Broglie wave number, and square of that would be what we have just discussed in the energy. Okay, so there is a characteristic energy scale in the system once you give me density. Now you can perform the analysis by introducing Fourier transform. So this should be phi, right, and the Fourier transform of the annihilation operator phi of x is written as ak. So this is an annihilation operator with momentum k. So what this will do is, if I have some bosonic state and if I hit ak on it, it will kill the one particle from the state, from the momentum state k. Okay. And these bosons they satisfy this commutation relations, ak a dagger k prime will be delta k k prime. So this is the correct commutation relationship. The one on the previous slide has to be corrected. Okay. So if I introduce all this notation, then what I will be able to do is I will be able to transfer the field, the Hamiltonian I wrote in the continuum, I can transform that into momentum language, and this will become some quantity which looks like this, which E of k is the kinetic energy of that state with momentum k minus the chemical potential. So this will be multiplying the number operator. So a dagger k ak measures the number of bosons in the quantum state, in the single particle quantum state k. Okay, so this is the statement. Okay. So what we are going to say is, we are going to say that there is an interesting phenomenon called Bose condensation, which occurs when you reduce temperature. And let me let the cat out of the bag here. We are just thinking that superfluidity is related to Bose condensation. So the idea is that these helium atoms are bosons, and when you cool them down below some temperature, it will Bose condense, and that is what you are seeing as superfluidity, etc. Okay, it is a ways to go to make that connection, but let us try to push it anyway. So for this I have to solve the statistical mechanics of this set of non-interacting bosons. So what I am going to do is I am going to set up a set of complete set of states to describe the states of many bosons, and the way we do this is by writing bosonic states that are eigenstates of the number operator associated with each momentum. So if I give you a set of occupation numbers of each of the momentum states, these are nks, which k is any momentum, and they can be any number 0, 1, 2, 3, n. I can generate a set of many body states with these nks which are given. For you have to specify the value of nk for each k, and then I will construct a fully symmetrized tensor product of that, and that will be the bosonic state. And these will be eigenstates of every number operator, every meaning for every momentum. And it will pick up the eigenvalue nk, which is what had entered in construction of the state. Okay. So from here, computation of the partition function is actually very straightforward. You know the energy of each state, and then you know the momenta. So they are independent, they commute with each other when k is not equal to k prime. So you can just simply do this. This is an elementary exercise. I am sure you have seen this before. So you just do this and you get this partition function, and you will get the grand potential, which is what is shown here. Okay. So now how do I have this unknown parameter mu, which we said we will obtain by setting up an equation to determine mu in terms of rho. And so if you work this out, since from here you can get the occupation of any momentum state, so you just take some suitable derivative with respect to ek, etc., and from there you can get what is the occupation number of the state. So once you get the occupation number, you immediately realize that you have that occupation number is simply the Bose distribution function. That is what is written here, right? And I am summing over all the states, and I am just finding in the thermodynamic limit, this sum k will become this integral, and I will be able to write down this equation. So the question is, of course, that if I want this all to be well defined, this quantity ek minus mu must always be positive. If this is negative, then I will have some trouble here, right? Then this number will become less than 1, and some negative numbers, etc., will show up here, and so on. Okay. So what happens if I try to solve this equation for any temperature given rho? So remember, if I give you rho, then there is a characteristic scale, there is a T0 scale which we have discussed. So you can think of temperature measured in the units of that T0 scale. And for whatever value of T by T0, I will be able to solve this value of mu in D equal to 1 and 2, spatial dimensions 1 and 2. You will find mu is always negative, and therefore that quantity ek minus mu is never less than 0 or even 0. So as long as the temperature is greater than 0, everything is fine, okay, in 1 and 2 dimensions. But the story changes when you go to 3 dimensions. What happens is, when I solve for this mu, you will see that the mu is fairly large and negative at high temperatures, high compared to like this T0. And then as I come in, reduce the temperature at about 6 times this T0, 7 times maybe, right, this mu touches 0, which means the k equal to 0 states, its ek minus mu has become 0. So now you see, if I try to increase mu now, then mu has to go positive, which means that there will be states in the system where ek minus mu is negative, which is problematic. So mu gets quote unquote stuck at mu equal to 0 if you reduce temperature, but then you will not be able to solve the number equation, and as Bose discovered and later confirmed by Einstein, etc., what one has to do is one has to place all those particles in the k equal to 0 state. So what this means is that the k equal to 0 state will start picking up a finite fraction of the particles, and the fraction of the particles is what I have plotted here. And you see, so for T greater than T BEC, so this temperature is called the BEC temperature, you will see that I will have there will not be finite fraction of the particles in the k equal to 0 state, in the 0 momentum state. And then at T equal to T BC, I start increasing the number of particles, it goes all the way up, and until at 0 temperature, all the particles are in the T equal to in the 0 momentum state. And you can easily work out that this fraction goes in this fashion. Now you will sit up and see that, oh, this looks very much like some kind of order parameter. I mean, this, if this is going linearly up here, but okay, that is a small difference, but overall this kind of curve looks like something that we have seen for an order parameter. So you might think that, oh, there is is there some symmetry breaking, or is there some phenomena like that going on here? Okay. So this is what we want to explore, and I will briefly discuss this. So how do we describe, or how do we find an order parameter for Bose condensation? Okay. So what is really going on in Bose condensation? So what one has to understand is that when E of k minus mu vanishes, when mu becomes 0, E of k minus mu vanishes at k equal to 0 for all temperatures below TBC. So what are the states of the 0 momentum sector? So you can have 0 particles, you can have 1 particle, you can have 2 particles, and each of those states labeled by n at k equal to 0 is created by hitting the creation operator corresponding to the 0 momentum state nk times, and hitting it on some vacuum state. So you can create this. Now remarkably, if you have mu fixed at 0, then all these states have the same energy, as you saw in the Hamiltonian that we wrote down. They have the same, they are all 0 states. So what this means is that the state with 0 particle, 1 particle, 2 particle, any number of particle state is degenerate. So the system chooses to linearly combine degenerate states with different particle numbers. Okay, without getting too much into the nitty-gritty of this, I can show you one such state where the different number of particle states are linearly combined together in a very coherent fashion. Coherent fashion meaning that there is a very distinct and clear phase relationship between the objects that between the coefficients of the different momentum, different particle number states. Okay, so this kind of state is called as a coherent state. So you can sort of think about it like this: you take any complex number phi 0, and you e to the phi 0 times the creation operator at k equal to 0 and hit it on vacuum. So you will get this state which is labeled by this complex number phi 0. Okay. So if you now work it out, you will see that it will combine each of these number states by a precise phase factor which is determined by phi 0, and there is a nice addition of there is a nice relationship between phase factor at one nk and another nk. Alright. Now I am going to claim that if you choose phi 0 is square root of n0. What is n0? n0 is that number occupied and so on, right, that number, where alpha 0 this is some phase, this is some phase of the state, this phi 0 is some complex number, it is square root n0, this one we have determined, and alpha 0 is an arbitrary phase which it has spontaneously picked up, much like the direction of spin in the Ising model. So since you are u1, you can pick up phase anywhere on the complex unit circle, it has picked up at alpha 0. Now if you hit the operator which changes the phase, right, that will not leave the state invariant. So under a symmetry operation which changes the phase of creation operators, etc., you see, so this is an exponentiation of creation operators, right. So you will see that if I hit every creation operator by e to the I theta, each of these will get different factors of, so the first one will get no factor, second one will get 1 factor, third one will get 2 factors, etc. So this new state that I will get will not be just a phase times the original state, and therefore a different state is what I will produce. So what I am showing you here is that this state is not invariant under the global U1 symmetry transformation. Because it is not invariant under the global U1 symmetry transformation, you are forced to conclude that you have broken this U1 symmetry if you put the system in this state. So the claim that I am making is that this phi 0 acts as the order parameter. It is a complex number, right, and that is the message that I want to convey, right. So this phi 0 by square root n, for example, will be a complex number, and this is what we will call as the order parameter of the broken symmetry state. You can of course confirm that the number of particles in this is equal to n naught, etc. Okay. So this is what I would like to point out. Okay. Now I want to flash a word of caution here. So without getting too much into technicalities and fine points, having Bose condensation alone is not sufficient for getting superfluidity. You need interactions between particles to get superfluidity. This is a very important point, and it's probably best discussed in a course on condensed matter physics, but this is something you should remember. We are making a connection between Bose condensation and superfluidity, but there is much more to the story than what I have shown you here. Okay. So we have come to the end of this lecture, and let me summarize what are the points that we have discussed in this lecture. So we have discussed that there is a very nice connection between liquid gas problems and Ising model, and you can model things like the liquid gas phase transition by just studying the Ising model with a suitable transformed set of variables. I discussed the experimental results on superfluidity of helium 4, and I pointed out to you that Bose condensation of an ideal gas occurs only in spatial dimensions greater than or equal to 3, and we pointed out that the order parameter corresponding to such boson condensation is a complex number. There are other important things that you must have observed while I was discussing this. You see, spatial dimension enters the story in a very critical way, in a very crucial way. You can see that in 1 and 2 dimensions there is no Bose condensation, whereas in 3 dimensions there is. Now you just think about what happened in the Ising model. In 1 dimensional Ising model did not have a finite temperature phase transition. Higher dimensional Ising model had ordered phases and disordered phases, and there was a phase transition between them. So you can see that spatial dimension plays a very determining role in what physics emerges. Okay. So this is what we have done in this lecture, and what you will see in the next lecture is that I will use both these elements. What are the 2 elements? The one is that liquid gas systems can be modeled by Ising like models, and that the order parameter of a superfluid is a complex number. I will use both of these ideas, and I will construct a model which will describe mixtures of helium 4 and helium 3. So I am sure you will be very excited to know how to use the ideas that we have developed in this course for explaining actual experiments, and this is what we are going to do in the next lecture. So please join me for that. Thank you.